in introducing chapter 32, instead of going in the order of the book, which starts off with Maxwell's equations and then moves into magnetism, I'm going to go ahead and start with magnetism and then go to Maxwell's equations, because Maxwell's equations lead directly into chapter 33, so it makes sense to talk about them at the end, and you don't need them to understand the magnetism part. So magnetism. Ultimately, magnetism in matter comes down to what's happening at the atomic level. We already know that magnetism is related to the electrical current. We know that this from Ampere's law. We know this from the equations we did before describing how magnetism works, and so. So we know that magnetism is related to the electrical current. So in an atom, we know that the atoms are not as simplistic as the Bohr model of the atom would have us pretend that it is. But in the Bohr model of the atom, we have the nucleus of the atom, and then we have an electron going around in an orbit. Now, it's really not this simple. It's absolutely not this simple. But the reason that we talk about the Bohr model of the atom is that it actually comes very close to explaining how atoms, how the atomic properties behave. Even though it doesn't get the exact what's happening in the atom correct, it does explain the properties that happen. And so that's why we actually do talk about the Bohr model of the atom quite a bit. So, in our discussions here of the Bohr model, we can imagine that the electron going around the atom, actually, the way I've drawn it there, the electron's going in that direction, going counterclockwise, that would have a current going clockwise. Remember, current goes opposite the way the electrons go. And so that would mean that we would have a magnetic field into the screen right there. And so we can imagine this as a current loop. Now, you know that there's a magnetic moment. The magnetic moment is going to be NIA. Well, N is going to be 1. I is going to be the charge divided by the time it takes to go around, so 1 period. And then A is pi r squared, where r is the radius of the orbit. Now again, this is a classic derivation of this classical model. It does not take into account quantum mechanics, which is what's really happening inside the atom. But it does kind of get the basic sort of concept down. So if I look at that, then the magnetic moment then would be minus E over T pi r squared. Okay. And we think about that, and we say, well, I'm gonna do a little algebra here. So minus 1/2, okay, E, and then 2 pi r over period times r. So what I did was I multiplied top and bottom by 2, and then broke things out. Now 2 pi r is the distance around. That's the circumference. The circumference divided by the period is going to be the velocity. So we could then say this is equal to minus 1/2 E V R. Well, if I multiply top and bottom by M, so this is going to be minus 1 over 2M times E times MVR. Well, where M is the mass of the electron. Well, MVR, we remember from physics 1, is angular momentum. And so we could then say that the magnetic moment here is going to be equal to minus E over 2M times the angular momentum of the electron. Okay. So that would give you the magnetic moment of this. Now, thing about this, in a completely separate discussion that's beyond really the level where we are at this point in the class, the angular momentum turns out not to be just any old number. the angular momentum, turns out to be equal to a constant times a quantized angular momentum. Niels Bohr realized that, for reasons that we'll get into later on, that that the angular momentum is quantized. It's not going to be just any possible value. So it's always the difference between angular momentum is always going to be equal to the same thing, h bar. So it'll be equal to some constant. We're going to call it m sub l times h bar. Now, what is h bar? H bar is h over 2 pi. Now, what is h? H is the Planck constant. We'll talk about Planck constant later on when we talk about light and the properties of light. So 6.63 times 10 to the minus 34 joule seconds. And that's the Planck constant. One thing we'll discover is the energy of light. If you talk about the energy of light, that's going to be the Planck constant times the frequency of light. But we'll be getting to that later on in the semester. But it turns out that same Planck constant that's associated with the energy of light is also related to the electrons in atoms. And then this actually kind of makes sense because light interacts with electrons. Light is electric and magnetic fields, as we're going to be discovering. And so the Planck constant divided by 2 pi, you see Planck constant divided by 2 pi over and over and over again in physics, and so that's why we come up with the term h bar to represent that. So m sub l is a constant, and m sub l is going to be 0, plus or minus 1, plus or minus 2, plus minus 3, etc. Okay, so this is going to be our derivation here of the magnetic dipole due to the orbit of an electron. Well, it turns out the electron also acts like it's spinning. So the electron is a small bit of charge that acts like it's spinning. And so it turns out there's a little bit of dipole moment due to the spin. So what we had before with the dipole due to the orbit, now we have the dipole due to the spin. Dipole due to the spin turns out to be also a constant times h bar, where this constant is equal to plus or minus 1/2. And so the electron can have a dipole moment in and of itself, just sitting there acting like a spinning charge, and then it can also goes around the atom. And so this gives you a little more complicated sort of scenario as to what's happening inside there. Now, how does this relate to magnetism on a large scale? Well, we have different kinds of materials out here. We have what we call diamagnetism, paramagnetism, and ferromagnetism. So we have diamagnetism, and we have paramagnetism, and we have ferromagnetism. These two are a little more closely related to each other in my mind than diamagnetism. Diamagnetism basically occurs with pretty much any material or any kind of substance, and that is that you've got these electrons, and the electrons are going, the proton, the nuclei, the electrons going around. You apply a magnetic field, and it kind of torques that magnetic moment, and it tends to want to line up a little bit with the magnetic field. And but it's a weak effect. It's not something that we normally would worry about. Diamagnetism in here. So with diamagnetism, then you apply the external magnetic field, and in most cases you have the magnetic moments all canceling each other, and so it really doesn't really matter much. Paramagnetism is a little bit more interesting. Okay. Um, um, with at least in my mind. And so paramagnetism, what happens is that so for paramagnetism, then what happens is that you apply the magnetic field and a whole bunch of these magnetic moments. So this would be some material that has a bunch of these electrons going around in the same direction. So you have this magnetic moment, and so what happens is that you have all these little magnetic moments, and they start all lining up in the same general direction when you apply an external magnetic field. That makes the magnetic field even stronger. And so we would have a magnetization. The magnetization, which is what you get here, is proportionate to the external magnetic field that you're applying. Okay, and it's going to be times a constant, and then divided by temperature. The higher the temperature, the more these things are going to be moving around and distorting sort of things. The magnetization is basically also equal to the total magnetic moment of this whole thing divided by its volume. And so it's going to be a property here of the material, and so that gives you paramagnetism. Now, what you get with ferromagnetism is a very similar sort of thing, except with paramagnetism, when you turn off the magnetic field, everything goes realigning the way that it was. With ferromagnetism, then what happens is that the neighboring domains interact, and you end up with little domains in the material that are all kind of similar oriented. And so you turn off the external magnetic field, and these tend to sort of line up still, and you retain a permanent magnetic field there. And so this permanent magnetic field is maintained. It's not as strong as it was originally when you had the external magnetic field on, but it's still there. And so this gives you the ferromagnetic property. Again, this is something that's destroyed by temperature. You get a high enough temperature, and these things are all going to like misalign. You shock it, you hit it, that also misaligns it. We talked a little bit about this in lab as to how these sort of properties are going to behave in here. And so again, with ferromagnetism, you turn off the applied magnetic field, and then it does not go back the way that it was. And so again, that's very similar to paramagnetism. Except with paramagnetism, it drops to zero. So here you turn off the magnetic field, and it doesn't drop back to zero. It drops, but not back to zero. So that's the basics of magnetism. We're not going to go in great depth here beyond that for this semester. We're just introducing the concept. We would go more into it if we had more time, if we didn't lose a week due to spring break. But so I'm just introducing the concept because we're supposed to be covering magnetism, and so I needed to mention at least a little bit of it. So now what we're going to do is we're going to start talking about Maxwell's equations.